Hey guys, we are doing the next section of Chapter 8. We are talking about confidence intervals still. In our first section, we learned just the basics of confidence intervals, how to interpret them. In this section, we're going to learn how to actually calculate a confidence interval for a population proportion, right? The whole goal is to estimate a population proportion. In our last section, we will talk about how to estimate a population mean. So by the end of this section, you should be able to both construct and interpret a confidence interval for a population proportion. And then we're also going to be able to determine the sample size required in order to get a particular confidence level or interval for a specified margin of error. And then how to describe the margin of error with the sample size and the level of the confidence. So please remember, this is our general formula for confidence intervals. You start with a statistic, which we know is our point estimate. Okay. And then we add or subtract some critical value times the standard deviation of the statistic. This adding and subtracting section, that's called the margin of error. Now, instead of saying the standard deviation of a prediction, we can instead call it the standard error. The standard error formula looks like this. Now, it looks really, really close to the formula for standard deviation of a sampling distribution. Okay, so the standard error describes how close the sample proportion will be on average to the population proportion in repeated simple random samples of size n. So if you're like, what's the definition of the standard error? Here it is right here. It describes how close the sample proportion will be on average. So what really is the difference then between the standard deviation of the statistic and the standard error of the statistic? They both measure the typical distance from the mean, but the standard deviation of the statistic, the sigma, is when we know the population, and the standard error is when we know the sample. So knowing p versus p hat. Okay? All right. Now, in that formula, you need to know the statistic, which is our point estimate. You also need to know a critical value. So we need to figure out how to calculate a critical value. We use z star. Okay, so it's not anything multiplying. We just use a z star, that is the symbol for critical value. The critical value tells you how many standard deviations we need to extend the interval to get our desired confidence level. So the star reminds us that it isn't a standardized z-score calculated from data. Okay, so that's the difference. We're not calculating it using that formula. We're finding it in a different measure. So for a 95% confidence interval, the estimated, keyword there's estimated, z star or critical value, is 2. Why do you think that's the case? Well, if you look at your notes, there's a beautiful picture of a bell curve with the empirical rule, right? Our 68, 95, 99, 7. So 95% of your data is within 2 standard deviations of the mean. So that's where this 2 came from. Now, however, that's an estimate, and we want to be a lot more exact. So how are we going to figure this out? So here's an example. Use table A to find the critical value z star for an 80% confidence interval. Assume that the normal condition is met. So since we want to capture the central 80%, that means we leave out 20%. So 20% is on the tails, and so 10% is on each tail, so 0.1. So you look in the body of your table to find the point where it has 0.1 to the left. Okay, so we do that and we see, hey, it's somewhere in between here. It's somewhere in between here, between negative 1.28 and negative 1.29. Now it's closer to this one right here, right? 0.1 is closer to that than it is to this. So we would say our critical value, z star, is 1.28. Okay, that is the closest one. So always go for the closest one. So let's do another one. What is the critical value for a 98% confidence interval? Well, if it's 98%, that means we have 2% on the tails total, meaning 1% on each tail. So using table A, you would look up now 0.01. 0.01. I actually want you to take a moment and figure out what that would be. Actually, no, it's right here. Sorry. It's 2.33. And we always use the positive, right? Even though it's negative on our table, we're going to use the positive version only, because that's how many standard deviations away we would have to go. Now I do want you, this is the one I want you to try on your own. Pause for a second, literally pause this video, get out your table, and figure out the critical value for a 90% confidence interval. When we do that, we should get, it's exactly halfway between 1.64 and 1.65. So when that happens, we can actually use the average of the two, and it'd be 1.645. Okay? Now, you can also, besides using your table, you can also use your calculator. You can use your inverse norm function. Right? If you go to second vars, you can use your inverse norm function, and you would just plug in the area that you wish to use. The most common intervals in z-scores, right? The most common intervals and their corresponding critical values. 99% is 2.33, 95% is 1.96, 90% is 1.645. You don't have to memorize these because you can always know how to calculate them. However, because they are used so frequently, it does help to kind of have them in the back of your head. When we're doing confidence intervals, we typically choose confidence of 90 or higher because we want to be quite sure of our conclusions. The most common confidence interval is 95%, but you might see confidence intervals of 80% or 96%. You could find it of any percentage that you choose besides 100%. All right, so let's get into the nitty-gritty. What are we doing? We are doing a one sample Z interval for a population proportion. This right here, if I could highlight it, I would. This right here is the method that we are using. So when we eventually do our whole four-step process, and it's like, what method are you using? This is it, a one sample Z interval for a population proportion. So what are we doing? We are choosing a simple random sample of some size n from a large population. It contains an unknown proportion p of successes. The approximate level C, confidence level for that proportion, is given by this formula. Right? Z star is the critical value for the standard normal curve. This is exactly like that general formula. It's just specific to proportions. Here's my statistic. Here's my critical value. Here's my standard deviation of my statistic. Okay? Now, when we do this, we're also going to have to test our conditions. So we've talked about two of these conditions in the last chapter. We know we need to figure out if it's normal, showing that NP and N times 1 minus P is greater than or equal to 10. Now, because we don't actually know the true population proportion P, we're going to use P hat instead. Okay? We also talked about independence, right? Individual observations are independent. When you sample without replacement, N should be no more than 10% of the population size. We call that the 10% condition. Now, the new condition that we have to test is the condition of random. So it either needs to say that it came from a simple random sample or it came from a randomized experiment. That will take care of the random condition. So we're going to go through our first example. It's very broken down. It's very broken down. This is kind of a step-by-step of how you do it. When we get to the next example, you'll see how it's all together. Students in an AP statistics class want to estimate the proportion of pennies in circulation that are more than 10 years old. To do this, they gathered all the pennies they had in their pockets and purses. Let's assume that this is random. Overall, 57 of the 102 pennies they have are more than 10 years old. So we're talking about pennies. We are going to do a couple things. We're going to identify the population and the parameter of interest, go through the conditions, actually do the calculations, interpret it, and then answer a question about it. These are basically the steps you're going to go through without them having to prompt you. So we're just kind of taking it slow to begin with. So let's start. Population and the parameter of interest. Well, the population here would be all the pennies in U.S. circulation. So not just all the pennies in the classroom, right? That would be the sample. We have all the pennies in U.S. circulation. The parameter, what do we want to know about those pennies? We want to know the proportion of pennies that are more than 10 years old. That's what we want to know. About the pennies, we want to know the proportion that are more than 10 years old. That's my P. We don't know it. go through the conditions. So we have 3 conditions: random, normal, and independent. We took a simple random sample of 102 pennies, so that takes care of the random. Check. We have to literally show the math for normal. So n was my sample size, 102. P hat is the proportion that our pennies are more than 10 years old, I should say. 57 over 102, so that obviously gives you 57. That's bigger than or equal to 10. Figure out n times 1 minus p hat, gives us 45. Both of those are greater than or equal to 10, so we can assume an approximately normal distribution. Check. Independent. Since we are sampling without replacement, we check the 10% condition. We can assume that there are more than, so times that by 10, we can assume there are more than 1,020 pennies in U.S. circulation. I feel like I have that many in my purse alone. So, independent, check. All 3 conditions have been satisfied. Because all the conditions have been satisfied, we can now go ahead and calculate and construct the 99% confidence interval. So, the first thing you need to do is to find the critical value. So like I said, if you don't remember it, you can use inverse norm. Okay, so when you do inverse norm, this section here is my area. This is my mean and my standard deviation. So you get a z-score of negative 2.576-ish. We'll use the positive version of that, positive 2.576. And then we're just going to plug everything into this formula, right? 0.559, where did that come from? That came from dividing 57 by 102. That's my p hat. This right here is my critical value. There's that p hat again. Here's 1 minus p hat. And then here is my n, my sample size. Okay, I did this first as far as calculations go, or you could just do it all at one time in your calculator, and you end up getting, when you subtract it, 0.432, and when you add it, 0.686. Pause this video and get your calculator and actually go through the math, because I want to make sure you can get the same values. It's one thing to know how to write it on paper, but if you don't know how to push the buttons in your calculator and get the correct values, that could be problematic. You should realize, since we're adding and subtracting a margin of error to our statistic, our point estimate, you should get a value lower than that and also a value higher than that. If you do not, that should maybe be a red flag. Okay. Also notice, because this is the proportions, you should get values that are decimals. Now that we've calculated our interval, let's go ahead and interpret it. We did this in the last section. We are 99% confident that the interval from 0.432 to 0.686 contains the true proportion of circulating pennies that are more than 10 years old. Please note that there are 3 things that are very important in your interpretation: the level, the interval, and the context. When you're interpreting the interval, you want to include the level of confidence, the actual interval, and then the context. Context is so important. Now, next question. Is it plausible that more than 60% of pennies in circulation are more than 10 years old? Yeah, it is possible. Actually, not possible. It's plausible, because 0.6 is in that interval, right? Our interval went from 0.43 to 0.69-ish. And since 0.6 is in that interval, that means it is a plausible value. So it is plausible that more than 60% of all pennies in circulation are more than 10 years old. That's a good reasoning there. Now, when we do our 4-step process, we're doing everything we just did. It's not prompting you. If this were a free response question on an AP test, right, you would have to do the 4-step process, including defining parameters as well as checking conditions. They count as things to remember. Now, a little way to help you remember besides state, plan, do, conclude is this little acronym. It's called PANIC, but I don't want you to panic, but I want you to do PANIC. So in your state, you describe the parameter. In your plan, you assess the conditions and you name the interval that you're doing. In the do, you actually calculate the interval. And then for conclude, you are concluding in context. Our next video is going to walk us through, and I'm going to show you exactly how we would do the whole 4-step process.